Okay, so here's what we were talking about last time. Actually, let me double check now. Yeah, okay, that's right. Okay, so we were talking about this theorem right here, right? This symmetry theorem, very powerful theorem. I used it massively in my undergraduate years as a in my physics courses. So we're going to do a lot of good stuff with this. Reminder of how to use this theorem. Both of the conditions have to be checked. This is a very dangerous aspect of the use of this theorem. It happens anyway, that students will see just a symmetric domain and get excited about that fact, right? And kind of forget to check whether the function is odd. And, then the theorem doesn't apply. It doesn't work, right? Or vice versa. Second thing to make sure that you're very careful with, and that is you have to be talking about symmetries over the same line. The line of symmetry of oddness for the integrand, the line of symmetry for the domain have to be the same line. Otherwise, again, the theorem doesn't work. Okay, so let's see, and we talked through the reasoning last time, and I think we had just barely started on this example before the bell rang for spring break. I hope everybody had a good spring break, by the way. Welcome back. So let's just start over with this example. And we've got a domain that's defined by, it's bounded by these two curves. Let's draw our domain. And here we go. Whoops. Let me try that again. Nice vertical line there. Okay, so here we go. This curve right here is something kinda sorta like this. Oh, I was doing so well. Let me try that again. It's something kinda sorta like that. Yeah, something like that. This, y equals -1, of course, is something like that. So the region that we're actually interested in here, the region bounded by those, is this region like this. And over that domain, we want to compute this horrifying integral. All right. So very hard problem if you come at this sort of brute force, right? If you do this iterated integral, it's going to be a nightmare. Okay. All right. So here is the first thing I'm going to argue. I'm going to argue that our domain is symmetric. Specifically, though, it is symmetric over the y-axis. Right? What that line of symmetry is matters for a combination of reasons. So anyway, there it is. The line of symmetry is the y-axis. Sometimes your domain might have multiple lines of symmetry, and that's nice and all, but you still do have to pick one. If you're going to make a symmetry argument, you need a line of symmetry. Okay, so let's see. Now let's talk about what it looks like to do a reflection over that line, and doing a let's see here. Let me do it with a pencil. Doing a reflection. If you have a point here, x comma y. And if you were to look at its reflection over that green line, this being your reflection R, notice that when you do that reflection, the y-coordinate doesn't change at all. The reflected point and the original point have the exact same y-coordinate. Right? This is a nice little observation to make about reflecting over a vertical line, is that the vertical coordinate doesn't change. So the y-coordinate stays the y-coordinate. The x-coordinate, I would argue, pretty clearly from, you think about the geometry of this picture, the x-coordinate is the negative of what it had been. And so x comma y goes to negative x comma y. So said differently, in the act of reflecting over this chosen line, the act of reflection just inserts a minus on the x-coordinate. Everybody with me? All right. So, let's see here. Let me clean up the mess here. Here is our formula for our reflection. Now, I claim I'm going to give you two arguments here. One is just an appeal to geometric intuition. If you look at this shape, it looks the same on the left as on the right. I mean, just purely geometric appeal. Looks like it's symmetric over the y-axis. Now, that may be satisfying to you? I hope it is. If it's not, here's the more explicit argument. Notice if you were to take this reflection and plug this reflection, for example, into that equation. In other words, instead of using x and y, use, well, negative x and y in that equation. This purple equation turns into this, which, of course, you can do some algebra, and lo and behold, it is the exact same equation. What this shows is that this purple curve is its own reflection, right? Because the reflected equation and the original equation are algebraically equivalent in the same equation. So that purple curve is its own reflection. I think it's even more clear that this blue curve here is its own reflection. After all, it's a horizontal line reflecting over a vertical line. That's just easy geometry there. So this shape is its own reflection. This shape is symmetric. Does everybody see how that worked? Now, I have some good news for you. When you actually get around to actually making symmetry arguments, this part here, where you demonstrate the symmetry of the domain, you're not responsible for. You don't have to do that. I include this here just so you can see what that argument would look like. This is to help you if you don't have a good geometric sense of whether your domain's symmetric or not. Arguments like this can help you decide, but you don't need to show that in your work. You do, however, need to note that your domain is symmetric. If you're going to use a symmetry theorem, you need to tell me that the domain is symmetric explicitly. And you also need to tell me what the formula for the reflection is. Now let's talk about the latter. Why do you need to show me the reflection formula? Well, because you've got to plug in the reflection in order to decide if your integrand is actually odd or not. Right? That's the definition of what it means for a function to be odd, is that when you put a reflection in, you need to get a minus sign out. So the value of the function at the reflection needs to be the negative of the value of the function at the original point. In other words. Now, there's a bunch of algebra that goes into this. I'm going to give you 2 points of view on how to think about this algebra. One is, again, you can literally take your reflection here, this negative x comma y, and notice that negative x is what's going to go into the first position. So negative x is going to go to, well, wherever the x was. And likewise, missed, sorry. Well, there we go. There and there. So negative x goes where x was. That's a little bit uncomfortable. It is, in fact, a confusion of variables. If you want to avoid this confusion of variables, here's the easy workaround. No big deal. Just rewrite your reflection here in terms of different dummy variables. Just rewrite it as r of s comma t equals negative s comma t. Right? And then you're plugging in colors again. Plugging in this reflection. Right, plugging that into the function, then no problem. Now you're plugging in negative s for x and t for y. No confusion of variables. You plug it on in. You do the algebra that ensues. Do be careful with that algebra. It's easy to accidentally oops some minus signs. Keep in mind, symmetry arguments are very delicate. It's very powerful. Lots of motivation to want to use them because you get to skip so much integration. It's awesome, right? But it's very delicate with the minus sign, so be careful. Cannot emphasize that enough. Anyway, the point is no confusion of variables, and confirmed the function is odd. How we doing? Everybody with me? Okay, and we are done. Integral is equal to 0 by symmetry. Okay. All right, now, there's a lot of moving parts then to being able to make a symmetry argument. I want to remind y'all, fundamental point of view on this class. This is not a class about answers. It's a class about reasoning, ideas, right? That kind of thing. So if you're going to give me a complete symmetry argument, I want to see all 5 of these points, right? So you have to tell me what your line of symmetry is. Otherwise, your argument's not complete, and it's importantly incomplete. I need to know what the reflection formula is, because once you claim, as you must, in order to be able to make a symmetry argument, once you claim that F is odd, in order to demonstrate that F is odd, you're going to need that reflection formula. Right? And then you also have to observe correctly that the domain is symmetric. Notice conspicuously absent. You do not have to demonstrate that the domain is symmetric. Again, if it's true, it's usually pretty clear, and I'm willing to trust that you have the proper intuition for it. No argument required for demonstrating that. Okay, but do be sure to give me all 5 of these points. I've already made the following point here, but let me do it again. Be careful when you're using a symmetry argument. It is very delicate. If anything goes wrong, then it goes off the rails so fast. Or even worse, you could accidentally put an argument onto the rails that shouldn't have gone on that should have gone off the rails. So, for example, if you have a function that's not odd, there is no symmetry argument, right? But if you miss a minus sign and it looks, based on the slightly sloppy algebra that you did, you accidentally got a minus sign wrong, and it looks like the function's odd, you're going to claim a symmetry argument that isn't there. And so let's think about what happens then if you're claiming symmetry argument, but there is no valid symmetry argument. You've reached a dead end. And it's not progress toward a solution. It's progress toward a dead end. And it's then I'm looking for by the way, I'm always looking for whatever excuses I can possibly dream up to give partial credit. And I can't if the work that you have is all in the wrong direction. So very dangerous. There's a lot of, what I call landmines in these kinds of problems, so please heads up. Now here's a kind of I'm going to call it a bad example. Question is to compute this integral right here, and the hypothetical student writes as follows: notes that the domain is symmetric, no justification given, no justification needed. Notes that the function has an odd symmetry. That is a true statement also. The student then immediately claims the integral is 0 by symmetry, and this student has done 2 of the 5 required steps. So notice, conspicuously absent from this work. The student has not even told me what line of symmetry they're talking about. That domain's symmetric over a bunch of lines. 4 lines. Yeah. Right? So which one are you using? That's not an argument if you don't tell me which line you're using, right? So this student has also not computed a reflection, and therefore can't and didn't demonstrate that the function was odd. Now the student did correctly observe that the function's odd, right? True. The student did correctly observe that the domain is symmetric. The student has done 2/5 of the required argument here. And, no promises on grading, but it's probably roughly proportional there. So, 4 out of 10, something along those lines. So, very important to give me the complete argument. And keep in mind, I've got these handy, checkpoints here. These are the 5 that I want to see for it to be a complete argument. Is everybody clear on what I'm looking for there? Questions? Yeah.
Is this particular domain symmetric across y equals x?
Yes, that's right. So the line y equals x is the line that is the line of symmetry that would make this a valid argument. So the student needs to say that, right? And then the student needs to give me the formula for that reflection, and I'll talk through how to do that on the next page. And then the student has to take that reflection and do the algebra to tell me that the function's odd. Yeah, yes?
Can you explain what it means for the domain to be symmetric again?
Yeah, so the domain is symmetric if it is its own reflection. Right, so that's what I claimed here, and again, I don't want to get into the weeds on, exactly how we know this. But if I look at this yellow domain here, and if I reflect that whole yellow domain over the axis, it's the same. Nothing happens. Yeah. So, yeah, different ways to say it. I think that's the most intuitively satisfying.
Thank you.
Yeah. Yes?
Saying that the domain is symmetric, is it the same as saying it is odd?
So that's a mismatch of type. So functions may or may not be odd. Sets are neither. A set is either symmetric or not symmetric over a given line. Oddness is a statement about a function and whether its values, when you reflect the input, whether you get a minus sign on the output. So it's specifically a feature of a function, not a set. Does that make sense? Yeah. Okay. Yes.
So you don't have to show through the equations that the domain is symmetric.
Correct.
You show the function is odd through
the function. Yeah, you do have to show me that the function is odd. So there's kind of two steps about the function, right? That's kind of the harder part, I think. So that's why I require both of those. For the domain, like I say, when you have a domain that is in fact symmetric over a given line, I think it's usually pretty clear, and I don't see the point in making y'all deal with that. It's just trivialities. Yeah.
If you have a domain that's like not symmetric, but a part of it is symmetric,
yeah.
Then can you say like by that logic, can you say like since that part is symmetric, we don't have to solve for one part?
Yes, you can. So now you do still have to give a complete symmetry argument for the part that you're claiming. In other words, when you carve it into pieces, the part on which you make a symmetry argument, you got to give me all 5 steps, and then you'd have just the leftover part that you could do by another method. Yeah. Okay. All right, so moving along, here's another example. And this is an example of what I mean when I say that it's usually pretty clear when a domain is symmetric. And I don't want to, let's not get into the weeds of how I would show this. But this curve here, curves, think of it either way you like, is what I've got there in blue. And I think it's hopefully intuitively satisfying that is symmetric over this 45-degree green line here. We can prove that if you want. In other words, we are going to write down the formula for the reflection, and you can plug it in and confirm that this curve is its own reflection. But you don't have to. But this is what I mean by it's usually pretty clear from the picture. Right? And then likewise, these two curves here, being as they are at right angles to the line we're reflecting over, they are their own reflections as well. Now, I did document this in the notes here. That, again, is just for communication purposes to y'all. This was not intended to be a precedent. You do not have to give me a symmetry argument for the domain. That's not required. Okay. All right. So let's see here. Next, let's look at we need to find the formula for the reflection. How are we going to reflect here? Again, reflecting over this 45-degree line like that, aka like this. Here's our, there's the line we're going to reflect over. How would I reflect a point that looks like this here? And if you look at the position vector for that point, well, that's at some unknown angle off of the reflection line. And so it's, what the reflection of that vector is going to be. It's really not immediately clear because it's some arbitrary angle. But here's the clever trick. Don't look at the position vector. Look at what I call a rectangular frame. That being this little sort of, half of a rectangle in blue there. How that reflects over this 45-degree green line, I think is pretty believable as being, well, it's just going to go like this. Right? Because I know that that's a 45-degree angle. And so when I reflect it, that's a 45-degree angle. That makes this a right angle. And that, because this is horizontal, that makes that vertical. Just the geometry works out really conveniently if you look at that rectangular frame as opposed to looking at the position vector itself. And with this rectangular frame drawn and reflected, you can now look at the reflected point, and you can practically read, its X and Y coordinates right off of that picture. And it's this right here. How we doing? Yep. Okay, so let's look at this line segment right here in yellow. Now that's at a 45 degree angle from my reflection line here. And so when I reflect it, this is going to be a 45 degree angle as well. And that makes this a right angle. And because of the fact that this was horizontal, that means that this is vertical. Does that make sense? And then analogously for, this was vertical, therefore this is horizontal. And since, since that distance is the same as that distance, and that distance is the same as that distance, I can then just look and see what the coordinates of that point are. And the coordinates of that point are that right there. Yeah. Okay, so there's always going to be a different geometry in every example. It's not going to always be like this. Instead of this line, we may sometimes be reflecting over that line, or we might be reflecting over that line. The geometry is always going to be different, but drawing yourself a picture is always one of the natural first steps. Yeah.
So to find the line of symmetry, do we just get it from the picture, or is it?
Yeah, it's usually from the picture. I'm sorry. Say your question again.
That was my question.
The finding the line of symmetry. There's different things that can motivate the line of symmetry that you're going to use. When the domain sort of, I'm going to say, geometrically presents itself with really only one natural choice, there's kind of no reason to look at the integrand and try to strategize from the integrand, because, this is the only line that could possibly work for both. It's the only one that works for the domain, and so if it doesn't work for the integrand, then we're out of business. Right? So, in a case like this, I think, yes, looking at the picture motivates the line. I am going to show you, however, another example in a few minutes where I think the integrand will be the tip-off. And there's some details that we'll need to get into then. So let me just defer that to that next example. Yeah. Okay. So, we're largely in business here. We take our reflection. There's our reflection. We plug that into the integrand. Be careful not to, accidentally trip on a confusion of variables. Again, if you want to replace, for the reflection, if you want to rewrite the reflection in terms of different dummy variables to avoid confusion, cool. Go ahead. Anyway, plugging that in, F at the reflection, algebra, and as desired, we get the negative of the original value of the function. So the function's odd. And we declare victory, right? We have a symmetric domain, odd function, integral is 0 by symmetry. And notice that all 5 of the requirements of the argument are here. Line, reflection, true claim that the domain is symmetric, no justification necessary. Claim that the function is odd, and demonstration that the function is odd. All shown in this reasoning. All right. Okie dokie. So, here's a dangerous example. This is one of the landmines you got to watch out for. Heads up. Suppose your domain is this triangle, and at a glance, we don't even have to draw the triangle. I can see that there's a couple of points where I got a 1 and a -1. Those are clearly reflections of each other, right? In some sense. Details, right? But that looks like there's a symmetry. And this triangle, just given the number of zeros involved, I'm highly optimistic that this is, in fact, a symmetric triangle. And in fact, it is a symmetric triangle. And then next observation, if you look at the integrand, that integrand is odd, as it would be suggested by that cube, right? By the 3 in the exponent there. And so a lot of students, I've seen this happen a tragic number of times, we'll see this, they'll go, oh, symmetric domain, odd integrand, boom, gotta love symmetry. Integral equals 0 by symmetry. but it's not. This integral is not 0. There is no symmetry argument. Any statements about a symmetry argument are just wrong, because there is no symmetry argument, because the symmetries are over different lines. The domain is symmetric only over the y-axis. The integrand is odd only over the x-axis. So neither symmetry argument, y-axis nor x-axis, neither one works. There is no symmetry argument. Yeah.
So I thought we checked if it was odd by sticking
the reflection.
Yes.
Yes. That's right.
So had we done this here, we wouldn't have been able to extract the minus.
Correct. So what I'm pointing out here is that the student who does not go through the details, the student who's playing fast and loose with the ideas, would be tempted to say, symmetric domain, odd integrand, boom, 0, right? When in reality, you're correct if the student had made a choice between these two candidate lines and then, drawn the picture and visually confirmed, wait a minute, is my domain symmetric over the line I picked? Or algebraically, as you described, had, explicitly gone through to see, is my function actually odd, like this 3 kind of vaguely suggests, then yes, you're right. They would have to bail, because one or the other of those is going to fail. Absolutely. Right. So think of this as a great example of why you should not go too quickly through a symmetry argument. This poor student here would get no points on this question, because nothing's right. Nothing is both right and relevant to an actual solution. Okay. All right. Good. Okay, 3 dimensions. It's practically the same thing. I'm going to go really quickly through this. Obviously, though, in 3 dimensions, we reflect through planes. This is how mirrors work, right? Anytime you look in the mirror, you are looking at a reflection through a plane. And here's you, and here's your reflection. It's exactly the same picture as in 2 dimensions. It's just 3-dimensional, and it's a plane instead of a line. The related ideas of oddness for a function and symmetry of a domain, exactly analogous. Oddness of a function means that when you put a reflection in, you get a minus sign out, just like in 2 dimensions. Domain being symmetric means that it is its own reflection, just like in 2 dimensions. Again, usually visually obvious if it's true. If it's symmetric, it's usually clear that it's symmetric. No argument required. Again, theorem. Integrand odd, domain symmetric, same plane, boom, we are done. Integral is 0. Walk away. Super powerful result. And with the same 2 usual warnings. You have to make sure that both conditions work. A symmetric domain is worth nothing by itself. Right? You have to check that the integrand's odd too. And vice versa. And again, it's got to be through the same plane for both of these requirements. Okay, so quick example. This kind of thing, I've done this a bazillion times in my undergrad. So let's take the unit ball. And by the way, the physical world is full of balls, as it turns out. They just come up all the time. So this kind of an integral is not at all rare. This is a routine kind of a situation to be in. And yet, I'll remind you that if you were to do this in rectangular coordinates, there's going to be square roots everywhere. It's a nightmare. If you were to do this in spherical coordinates, there's a massive amount of trig in here. That's no fun. It's doable. You can do it. I would do this in spherical coordinates, but it's still, you're going to have a lot of cranking to deal with there. So neither one of those is particularly desirable. So check out the symmetry argument, though. I'm going to choose the XY plane. I'll come back and tell you why in just a minute. This is get back to your question. So let's just trust me for a moment. Let's take the XY plane. When you reflect through the horizontal XY plane, if you think about what that means to reflect through the XY plane, the Z coordinate gets a minus sign. Right? So this implies this. And you can plug this into your integrand here and do your appropriate calculation, and lo and behold, you do get a minus sign here. So this function is odd. We're integrating over the unit ball, which is obviously symmetric. And so, boom, integral 0. We're done. Right? Snap of a calculation. Way easier than even the spherical coordinates alternative. Yeah. Oh, you're good? Okay. All right. Yeah. Okay. Okay. So here's the thing I want to come back to. So where did I get this from? Why did I pick the XY plane? Did I just dream that up? Was it random? No. There's actually a good reason that I picked the XY plane. So this gets back to your question from a while ago. I claim I reverse engineered this choice as follows. I was looking at my integrand and I saw this 3 and I'm like, I like 3s. 3s are odd. I love odd. Odd suggests symmetry argument. I'm getting excited here. Oh my gosh, it's possible symmetry argument. This makes me think there could be a symmetry argument in play. After all, a -1, when you cube it, stays negative. That's that minus sign that you need. Right? So the 3 makes me wish that when I whatever plane I pick, I want to get a minus sign on that z, so that minus sign can get cubed, which leaves me a minus sign. Right? So this 3 right here motivates that I wish, I don't know anything about the plane yet, but I wish this was my reflection formula. Right? This 3 here motivates, wouldn't it be nice if this was my reflection? And then I just have to think geometrically. Well, if I here's my XY plane, and if I have a alleged reflection that goes, whatever point I have, I just put a minus on the z coordinate. What am I reflecting through? Well, I'm clearly reflecting through the XY plane. So this then motivates the choice of the XY plane. Right? Is that good for everybody? So sometimes this is how it works. Sometimes it's the domain that suggests your line or plane of symmetry. Sometimes it's the integrand. And in this case, it was the integrand. Of course, again, you need both. The reason I use the integrand here is because my domain kind of gives me too many choices. My domain's it's a ball centered to the origin. It's symmetric about countless planes. Any plane through the origin, right? That doesn't help me. It's too many options to help me whittle it down. The integrand, I think there's really only the one option. Okay, so you make sure to look for both. Okay, that's 5.5. Yes, question.
Well, the cube.
Yeah, the cube.
I'm struggling to see how we make the jump from it. Since we have a cube, we wanted.
No, but wait a second. Are you talking about this example?
Yes.
Okay, so there's no cube in this
In
example.
the z cube.
Oh, the cube. Oh, I'm sorry. Yes, thank you. Go ahead.
I don't think I fully understand how we made the jump that we want our reflection formula.
This, okay, yeah. Because I was kind of anticipating this algebra, right? And in particular, I was thinking, okay, this cube here is going to go there in this process. And if my reflection gave me a minus sign here, then I would see, well, I'm going to have a minus cubed, and a minus cubed is a minus, which is what I want. Does that make sense? And so, okay, well, now how am I going to get this minus sign here? Well, that minus sign needs to come from the reflection, right? Because that's what we plug into our integrand is whatever the reflection is. Does that make sense? Yeah. Cool. All right. Okay, so I've lost track of how many lectures we spent in section 5.5. We finally made it through, and we're moving on now to 5.6. Okay. So there's a bunch of. Oh yeah, go ahead. Question.
For the midterm,
Yeah.
are we just going up to 5.5?
It depends on how much we finish by whatever I have on the calendar. Ask me after class. I can clarify. I think it's going to depend on what we finish Wednesday. I can't remember. I can't remember. But we'll talk about it after class. Yeah. Okay. So, yeah, in section 5.6, there's a mishmash of different topics that are all kind of related to each other. Some of them are math ideas, some of them are physics ideas. I'm going to try to keep the physics to a minimum. This isn't a physics class after all. That said, it is nice to have physics applications so you can see what the math is, good for. The way some students think about it. And also, in some cases, the physics itself motivates some mathematical choices. So, but in every instance that physics comes up in this section and in this course, the purpose is for the physics to support the understanding of the math. It is not to learn physics for the sake of physics. So, keep that in mind. Okay, so starting with what's called a weighted average. So this is an idea that I hope you might already be comfortable with. If not, it's important that we get you comfortable with it because after all, this is how our course grades are computed in this course. You may recall weighted averages of the exams and the homework and the attendance and the final exam, etc. And the weights are all set and etc. So let's talk about what that means. So here's how I average 6 numbers. Ancient history, old news. Right. Let me expand the 6 here. The whole point of where the 6 came from is that's how many numbers there are in the numerator. So the number of numbers up here is the same as the number of ones down here. And then I can kind of group them and say, all right, well, this business here, I'm going to streamline by just observing that I'm multiplying 4 times 2. And then the denominator, I get a 2. And then with the 7, well, okay, it only appears once. And then with the 8s, well, that 8 gets multiplied by 3, and there's 3 in the denominator. So notice then that this construction that I have in yellow, which I'm rewriting with sigma notation down here, this construction is really just a way of saying, I want to average these numbers, and 4 is one of the numbers, but I'm counting 4 twice. So this 2 here, which is one of the W numbers down here in this notation here, this 2 is telling me how many, it's a representation of the fact that the 4 is double counting in the average. And likewise, this 3 here is a representation, again, that's what we call a weight. This is a representation of the fact that the 8 is triple counting. That's all it is. Yep. Okay. Now, once we've motivated this formula on the basis of double counting, triple counting, etc., then I point out that, written in this form, there's no particular reason that the weights have to even be integers. I can just think of these weights as, in some sense, being an indication of how much of an impact do I want that value, whatever V value that is, how much of an impact do I want that to have on the average I'm computing. So this, up here, the 8 has a triple impact of 3, right? Happens to be an integer. No reason in this formula that it should have to be an integer. Okay, so let's see some examples. This one is about grades. Again, close to our circumstances here. And now this is not exactly our course weights, but we've got Bob anyway here is going to have 4 exams, and they're weighted like this. Just keep it simple. The weights in our class, again, there's a 7 and a 3, and the numbers get weird, and there's no need to complicate the arithmetic here. So anyway, here we go. We have 4 exams with these weights, and Bob gets certain grades on these 4 exams, and he wants to compute his course average. Of course he does, right? So how does he compute his course average? Well, the weights go right there where the formula says they go, right? Those weights, I'll do it like that, go right like that. The grades that we're averaging, right? These grades that we're averaging go there, and there. And arithmetic and answer. And so Bob's course average is approximately that number, whatever that is. How we doing? Everybody with me? Okay. Now, just real quick about our course. There's also the question of, okay, well, yeah, but this isn't exactly a 3, and it's also not exactly a 2.7. It's not exactly any of the standard grades. So how do you turn this, decimal into an actual letter grade? And in our course, that's done with bins. The bins are approximately, not exactly, but pretty closely, just which of the standard reference point numbers is this closest to. And of course, this is very close and certainly closest to 3.0, so Bob gets a B in the class. Does that make sense to everybody on the arithmetic? Okay. All right. Okay, here's a harder problem. Suppose I don't have a finite list of numbers. Suppose I have an infinite list of numbers as follows. Suppose I'm looking at the values of a function. Let me do it like this. The values of a function, such as, for example, something like that. Here's a function. Look at this green curve. We're looking at the graph, by the way. What's the average of all of those values of the function? Now, here's the thing. The values of the function, well, golly, the values range all the way from this lowest value to this highest value. How do I average an infinite number of... I can't add up all infinite number of numbers, right? I guess I could average the endpoints or something, and that would put me there in the middle, but I feel like that somehow ignores the complexity of the fact that there's a curve there, right? How do we incorporate the curve? So the big idea here is to recognize that if I were to break this up into pieces, for example, let's look at how often it is, how long is the curve in this range of values here? Well, the function is in that range of values, roughly from there to there, right? The function is in that low range of values for a lot of the domain. Whereas, by comparison, if I were to look up here, an equally sized sort of piece of the target there, the function is in that range of values for a much thinner, I didn't do my art there super well, but you get the idea, much smaller part of the domain. Said differently, this green function, it is sometimes equal to these values, but not very much. Not a lot of input values. The function does not take these purple values up here much at all, but the function takes these dark blue values down here a lot. Right? So what I'm going to do then is I'm going to argue as follows. Yeah, I want to average the output values of the function, but I want to use size in the domain as the weights. The function takes these values over here. For more of the domain, I want it to weight more. And likewise, less over here. The function doesn't take these values hardly ever at all, so weighting it less. So altogether then, weighting by size in the domain, I claim that that's what this expression here does. It weights by size in the domain, dx. And the values that we're averaging, well, the values of the function itself, sure, all of these values. Right. Those are the numbers that we're averaging. Weighted by size in the domain. And that gives us this expression right here. Sure, it's an integral instead of a summation. Well, there's a continuum of different values here. But same concept as a weighted average. Okay. So, we can compute. By the way, notice, nice little simplification. It's convenient. So we can compute, for example, this expression, if I want to take an average value of sine x between 0 and pi, right? Notice all I've done is I've plugged in the, what is it that I'm averaging over what range of inputs, and we've got a single variable integral that I can just punch up, a little bit of calculus there. Answer's 2 over pi. Everybody with me? Okay. All right. Same thing in 2 dimensions. It's just, question.
So we just use this integral approach when we're not dealing with a bunch of points.
Well, if you're trying to find the average value of a function, yeah. And so this is one way that you might have a continuum of values. Yeah, but specifically this formula is for averaging the values of a function. Yeah, totally. All right. So, shockingly similar in 2 dimensions. If we're in 2 dimensions, though, function of 2 variables, size is no longer length. Size, aka our weights, are now areas. So this is totally analogous to what we did in the single variable case. It's just that now we have double integrals to deal with. The denominator is now the total area. And this formula right here, I can do in an example. Specifically, let's ask what's the average value of this function over this domain, the unit disk. And okay, so some, calculation ensues, and there's integrals to compute here, and I think polar coordinates works pretty well, and it works out with a nice but shockingly round answer of 1/4. Even though when there's a unit disk involved, I'm kind of always concerned. Here comes the square roots, here comes the trig, right? Something ugly is going to happen, so it's always a little unexpected when the answer turns out nice and clean like this. Okay, moving along. Center of mass. Now, this is a physics idea. You could argue this is a physics sort of application of average value of a function. We're going to define, in fact, center of mass as being a weighted average. Let me do it like I'll do it like this. It's a weighted average. It's literally a weighted average of position. I'm averaging the x coordinates of whatever it is that I'm looking at. But, I need to use weights. Obviously, the heavier piece of mass over here, it's got more weight. That should contribute more. It should weigh more heavily in the average. And this smaller piece of mass over here should weigh less in the average. So we're just literally going to use the masses as the weights, and this thing we call center of mass is that weighted average. So nice little formula. Again, you can generalize this to a continuum as this. Right, same idea. And again, the denominator simplifies very nicely. That's just total mass. And so here's our formula for center of mass. There is one little sticky wicket on this, and that is that this expression here involves, you see right in here, technically something we haven't defined yet. This is not a big deal. It's nothing to worry about, and I don't want to kind of get into the weeds on the formalities of it all. But we have here a vector integrand. And we've never talked about an integral with a vector integrand before. Here's the good news. If you think about what an integral does, you're just adding stuff. Now you're multiplying by scalars. Adding and multiplying by scalars is always done one coordinate at a time. And so when you have a vector integrand, you can compute the value of that integral one coordinate at a time. Right? So, comma, ... comma. Just look at the x1 coordinate, and then the x2 coordinate, and the x3 coordinate, etc. And the resulting vector is the integral of that vector. And of course, don't forget to distribute your scalar out front. So what I'm going to say exactly what you would think it would be. Okay, and I'll bet you we are out of time now. Yes, we are. Okay, so I'm going to draw the line right there. We'll finish with this example Wednesday. And see y'all later. Don't forget to stick around and make sure I mark you down as present if you came in after I did attendance. See y'all later.